Good afternoon, and thank you for joining us for this rapid fire showcase. My name is Broc Burke, and I'm with Washington University in St. Louis, and today I'll be discussing how we've been working to illuminate ischemic stroke using near-infrared spectroscopy. I have no disclosures, and I would like to start by giving you some background on why we decided to perform this study. As many of you are aware, stroke is a major health issue both in the United States and internationally. What you may be less aware of is, as early as 2010, correlations between the functional connectivity in the brain using MRI were being shown by Carter et al., while nearly at the same time in 2009, White et al. Were showing similarities between the results of functional connectivity MRI and functional connectivity diffuse optical tomography, which uses that near-infrared spectroscopy that I was mentioning. Now, why would we try to look at results using fcDOT? Well, it's significantly less expensive, $100,000 versus $3 million, and it's portable enough to make it bedside, which becomes really interesting when you realize you could have the potential of using it as a monitor as opposed to the current Q1 or Q2 hour neurochecks. Now, what you'll see here is the wavelengths that our system is using. We're using 750 nanometers shown here and 850 nanometers shown here, basically giving us sensitivity to both the oxyhemoglobin shown in red and deoxyhemoglobin shown in blue, while being outside of the absorption spectra for lipids or water. Furthermore, we're using the same physiology that is exploited for fMRI, where we know that given a stimulation, whether that's finger tapping, some noise, speaking, that you then have an inrush of oxyhemoglobin in a given region and a corresponding decrease in deoxyhemoglobin. With that information, if you put together a system similar to that shown on the left, which is what we were using for this study, then you can get an image that you see on the right, which is the time course of that activity over time. Now, I've been talking about functional connectivity, and what that is the temporal correlation from one area of the brain to another. So, looking at that red circle, you see the time trace of the activity for that red circle. And then on the contralateral side for the orange circle, as you would guess, given bilateral connectivity, they're going to have similar time courses as shown by that correlation coefficient of 0.52. Now, if instead I looked at the correlation between that red circle and the blue one, then I have less functional connectivity, or in other words, less temporal correlation over time. The next step that we did is we looked at what the functional connectivity looked like in stroke as compared to normal subjects. So in that top column, what you're looking at is first the field of view for our system, and then in each one of these, you're going to notice a black dot, which is what we're using for the time course to compare for the rest of that image. And in this case, in that top row, you'll notice that you have that bilateral connectivity, and no surprise that within the areas directly adjacent to the seed, you also have functional connectivity. So that middle column is the right motor seed column, and then the far right one is the visual seed column. Now, the next thing that we did is I've given you 3 example stroke subjects with NIH stroke scales of 2, 17, or 27. So getting worse as we go down the screen. And as you would likely guess, the size of the infarct shown in red for these CT scans is larger for each one. And a different way of looking at it is just projecting that out to the gray and white matter interfaces. Now, what you'll additionally see is with a relatively small stroke, the bilateral connectivity is relatively well intact for both the motor and the visual seeds that we're showing you here. For the mild stroke, then when you go up to the NIH stroke scale of 17, that motor bilateral connectivity fell apart. However, the visual was still intact, and then it goes away completely when we're looking at the severe stroke. The next step, given that I was just showing you example functional connectivity maps there, is to do a spatial correlation of those against young healthies, and then also doing that for age matched. When you do that, you end up with a similarity measure. Now, if you look at the similarities for our age matched versus our stroke, you have a nice separation as shown both by the p-value and the strength and just visual inspection. Similarly, if you looked at the similarity versus the NIH stroke scale shown at the bottom there, we also end up with a nice correlation, again shown with that p-value and the r-squared value there. So in the end, I've shown you that we have that correlation of the Similarity NIH Stroke Scale, and I'd like to thank the NIH, IARS, and everybody in the lab. Thank you for your time.